Good morning, everybody. If you can go ahead and give me a green check mark. Ooh, Josh, you're on that check mark like that. It's a good, quick check mark. Just let me know everything's working okay this morning. You can see the video and audio and everything's good. Perfect. All right. Today, what I want to do is I want to continue on with Unit 8. I would like to begin with any questions you might have had from 8.1. There's probably a few. Remember last day we were talking about distance, displacement, position, and these are kind of the three sort of big vocabulary terms that we'll talk about. We're going to talk about them a little bit further today when we start dealing with velocity, and it's just kind of more of the same. We do a little bit of calculations and stuff again today using some formulas that are in your data book. And it's kind of where we're at. So I said that I'd probably have a final exam sort of sorted out by either today or next day. I've decided that I'll probably make it between 30 and 40 questions, and it'll be mainly on units 4, 5, 6, 7, 8, and 9. So those 4, 5, 6, 7, 8, 9, 6 units. And so it'll cover chemistry, it'll cover radiation, and it'll cover the physics stuff we're doing right now in sections 8 and 9, or units 8 and 9. I haven't made it yet. When I do make it, I'll give you an exact breakdown of which questions come from which units and how many, just so you know. But a traditional provincial exam has 60 questions on it, and that's supposed to take you 2 hours-ish. It doesn't take that long. And then you get that additional hour. So I figured if I cut it in half at about 30 questions, you guys should have no issues finishing in the hour-ish. I think we have booked from 9 to 11, so you get the kind of an hour to do it and then kind of an hour to, tie up any loose ends. So that's that. Thank you for putting questions in chat. Costin, do you want to throw in a specific question? That would be a little bit easier. And we'll jump into the learning guide, section 8.1. Thanks, Costin. And we will go through some questions there, and then we'll look at 8.2. We might do 8.3 today as well. Let's just see how long it takes to get through all this stuff. And I mean, the sooner we finish, the more time we have for review. All right, so question 2, page 1, and then number 4 on page 1. Under what conditions is the magnitude of an object's displacement the same as its distance? Is that question 2, page 1? That was Kyle. All right, so the magnitude of an object's displacement the same as its distance. All right, so I'm just going to draw a little picture here. Let's say we have a house, and then we have like a tree over here. There's my nice little diagram, and we're talking about distance and displacement. Remember, distance is just how far you traveled, and displacement is your change from where you started to where you ended. So, Josh, you're a step ahead of me, and you're right. Let's imagine this. I'm a little person here. Here I am, a little stick person. I walk to the tree, and then let's say I walk from the tree back to the house, and I don't know, maybe this is 1 kilometer. So the distance traveled would be 2 kilometers. 1 kilometer to the tree, 1 kilometer from the tree back to the house. But my displacement would be 0 because I started and ended in the same spot. But what Josh is demonstrated here is that if I just walk in one direction and I go from the tree to the house, and this is 1 kilometer, because my displacement, my start to finish, Because they're in the same direction, I haven't changed and turned around and walked back to the house. My distance is 1 kilometer, and my displacement is 1 kilometer, and we'll go with east. So the magnitude of my displacement is the same as my distance. They're both 1 kilometer, and the question's specifically asking under what conditions, and you can travel in one direction, essentially. That's not as handy as you'd hope for. Travel in only one direction. So that would be the series of conditions. That as long as I go one direction, I don't turn around and go back or go north or some other direction, they'll be the same. So that was question number 2, page 1. Costin's asking about question number 4, which we did in class-ish, talked about it last day a little bit. So this little chart talking about the difference between scalars and vectors. Remember, vectors are things that have a direction associated with them. So as soon as you see square brackets with things like southwest, north, down, downstream, up, those indicate a direction. And as soon as you have a direction associated with something, it's a vector. If it has no direction, like time, weight are 2 big ones that don't have any direction associated with them. Distance doesn't have a direction. Speed doesn't have a direction. So time, weight, distance, speed, these are all things that have no direction associated with them, and we call those scalars. It's just some fancy physicsy words to describe things. Can 3 vectors of different magnitudes and directions add to 0? Show with a vector diagram. All right, 3 different vectors, different magnitudes and directions. Add to 0. I'm thinking yes. Let's say I started here. I want to start and end here. So if I had like something that went down there, and then something that went there, and then something went back there, I could conceivably travel in 3 different directions. And as long as your triangle's not isosceles, you'd be okay. Let's make it really, really obvious that these are 3 different lengths. All right, so I have that first arrow there. Maybe I'll draw a little arrow straight up, and then I'll draw another arrow back to the start. So those are 3 different arrows. When I say add to 0, it just means that they start and end at the same point. So yes. There's my vector diagram. Vectors are just arrows. 3 arrows that start and end at the same spot. There you have it. Was there anything else from 8.1? You're welcome. Anything else from 8.1 that you guys had any concerns about, issues with, didn't understand, want to go through? If not, we shall move on. All right, let's jump into 8.2. And 8.2 is velocity. And velocity you've likely heard about before, the word velocity. What does the word velocity mean? Can you think of maybe what you've maybe when you've heard the word velocity before, sort of what context that was in? Has anyone heard of the word velocity before? Is this kind of a new thing? Velocity. What does it mean? What kind of context have you heard the word velocity? No ideas, hey? That's interesting. That's all right. That's all right. Speed, yeah, so velocity and speed are very closely related, Jesse, and we'll actually talk about the difference between these two words, which is not probably that big of a difference, but it is a difference. So definitely has to do with speed, movement, velocity. You can talk about like maximum velocity. Maybe you've heard of the word terminal velocity before. These are kind of things that are important. I guess not important, but common. So, first thing, speed. Jesse let us off with this. Speed is the distance an object travels during a given time interval. What a kind of a really hard way of saying just how fast something's going. So when we get into science definitions of things, we got to use all proper vocabulary, but just speed is just how fast you're going. You're driving down the street. You guys are all grade 10. I would assume most of you probably have your learner's license by now. Do we have any late birthdays that haven't got their learner's license? Got a truck. Well, that's good, Costin. Kyla, are you a late birthday, or do you have your learners already? October. My son's birthday is in October as well, so he'll be a late driver as well. Costin's October. There you go. So you're thinking about driving, some of you. I'm pretty sure, Eric, you have your learners, right? Is that right? Yeah, nice. All right. So when we talk about speed and velocity when you are driving, it's very important. You have speed limits, and those are posted on the sides of the roads. You've seen them before. Most city streets are 50, some school zones 30. You go on the highway, it's 80. You drive to the coast, it's 120 now. So what do all these numbers mean? We also have another word for speed, very closely related, velocity. And the only difference between speed and velocity is that speed doesn't have a direction associated with it. 50 kilometers per hour, done. That's the speed limit. But when we talk about velocity, we're just including a direction with it. So if I said 50 kilometers per hour forward, there you go. You have now a vector, you have a velocity, you have a speed and a direction. So speed and velocity are essentially the same thing. If you have a speed, no direction, it's a speed. If you have a speed with a direction, you can call it a velocity. So velocity just tells you how fast you're going with a direction associated with it, essentially. So velocity is a vector, speed is a scalar. And this is a little bit different than sort of everyday life and things like that. When we talk about speed, sort of a context of our lives, generally we're talking about speed limits in cars, how fast things were going. You just about always talk about things in terms of kilometers per hour. How many kilometers can you travel in an hour? That's the speed. 100 kilometers per hour means in an hour you're going to travel 100 kilometers. When we start scaling things down with cars are big, they travel fast, you can travel many kilometers in a given time. But when we start talking about things like objects moving, like people, if I were to walk down the street, I probably would walk, I don't know, how many kilometers could I walk in an hour? Maybe like 5, 10 kilometers in an hour. The numbers just get really small. Now if I was just rolling a ball across my desk here, that's even smaller. It's not going to travel any kilometers in an hour, and it wouldn't travel for an hour. It's just traveling for like a meter for a few seconds. So when we talk about most questions in the course that we'll deal with, they're going to be using the SI unit, which is meters per second. So just like kilometers is a distance per hour, we just kind of scale it down to kind of the human scale. We're talking about meters in a second. And we'll learn how to convert back and forth between meters per second, kilometers per hour. So this is on the back page of your data booklet. It's on page 12. It is at the very bottom of the page. So at the top of the page, you have your common isotopes pairs chart, your radioactive symbols, and then at the bottom you have these two little tables. And these are the important terms and formulas that we're going to use in the physics unit, both units 8 and 9. So you can see distance as usually measured in meters. We can measure time in seconds, minutes, hours, or years, and it gives you the symbols there. For today, we're going to just do the first column of the table here, equations of motion. We're not going to do acceleration until unit 9. So the second two columns of the table, equations of motion, we won't encounter until next day. So essentially we have three formulas. You don't have to memorize them, they're given to you, and we're going to end up using these. The idea here is that velocity is how far you're traveling divided by how long it took you to travel there. And it kind of makes sense if you talk about a velocity in kilometers per hour. You have a distance 50 kilometers. That's how far you'd go in 1 hour. That's a speed or a velocity of 50 kilometers per hour. That's what the formula is how far did you go and how long did it take you to get there. Sometimes we're going to be interested in how far you went. Sometimes we're going to be interested in how long it took you to get there. And sometimes we're going to be interested in how fast you were going. So that's the three sort of variations of the formula. And when you're in grade 8 or 9, you study density, maybe even 7, I think. And density is the mass per volume. And you get these little triangles. Has anyone seen a little triangle like this before with an equation? You kind of cover up what you want to try to find. Jesse has. Was it density, Jesse, or did you deal with it in something else? Usually density is the first sort of thing you probably encounter. That has to do with this sort of thing. Yeah, all right. Let's see if I can find my cursor here. All right, so we have this little triangle, and it has the three different things in it. We have distance, we have time, and we have velocity. Now, these equations are all given on your formula sheet, but sometimes it's kind of handy to use the triangle. And the way this works, the easiest way to think about this is whatever you're trying to find, you just cover it up. So let's say I wanted to find time, and that's what this little diagram's showing. If you want to find time, you just cover it up with your finger or whatever. And what's left? Well, I have a distance on the top up here, and then this is kind of like divided by this line and then velocity. So if I cover up time, what's left? Well, I have d over v. And I can do the same thing. If I covered up velocity, v, I'd be left with d over t. And if I covered up d, I'd have velocity and time next to each other, and because they're next to each other, we're going to multiply them. So it's just kind of a handy little way to remember it. And you can see in the other picture here where we've covered up time with our finger, we have distance divided by velocity, so we get our formula. Time is distance divided by velocity. So we're going to use this, and if I go back just real quick, you can see that we have the same formula with all these fancy triangles in it. We have time equals distance divided by velocity. So that was the formula we just looked at from the triangle. They're all three formulas are given there, so you don't have to memorize them. But sometimes it's just a little bit faster to cover something up and look what's there. All right, so the big idea is here. Speed is just how fast you're going, no direction. Velocity is how fast you're going with a direction. Instantaneous velocity is just the velocity at a given instant in time. So instantaneous velocity becomes more important when we start to deal with acceleration next class. And then average velocity is just how far you went divided by how long it took you to get there. So they all kind of look like they have different sort of definitions, but in reality they're all pretty much the same thing. All right, so let's look at a couple examples, see if we can use these formulas from the data book to try to figure these out. So what's the average velocity of a dog that takes 4 seconds to run forward 14 meters? So if I jump over here to OneNote, I can start filling out some of these. All right, if I think about what I have in the notes, I had this triangle. Here's my triangle. I have velocity, distance, time. I don't know if I've ever mentioned this before in this class. I'm trying to think if I have or not. I know I talk about it in grade 8 science a lot. When I write the letter T for time, like normally if I wrote the word time, I'd write it like this, time. My T would just look like that when I write sort of every day. But when I write the variable for time, I always give it the little bottom. Because in physics, plus signs and T's start to look very similar. Especially when your writing is as messy as mine, it's kind of good habit to get into to write your T's with like a bottom on them like that. Just so you're never confusing the letter T with a plus sign, because they look the same. And I'll give you an example. This is an equation you won't see until physics 11, but in this equation, right here, you have the letter T and a plus sign right next to each other. So if you wrote it as D is V naught T plus 1/2 A, let's change this T, T squared, things start to get really confusing. Is that a T? Is that a plus sign? Why is the plus sign squared? What's going on? So just kind of good habit to start writing your T's like this, because you're never going to confuse that T with a plus sign unless things get really, really messy and out of control. All right, so the thing that I can recommend to you for these questions is, I mean, the sort of beginning ones are fairly basic and you probably get them without me trying to spend hours explaining it, but just in general, when you're doing these questions, the best thing you can do, I find, is go to the question and try to figure out what information you're given, try to figure out what you're trying to find, and then you can use that information and a formula to kind of work together to solve for what you need. So the question here says, what is the average velocity? So that means I'm trying to find average velocity. And the way that we'll write average velocity is v with a little av, like a little subscript next to it. And that's just average velocity, v average. We're going to also write things like v with a little 0 next to it for initial velocity and v with a little f next to it. And these are subscripts, just kind of to keep things sorted out. So we're trying to find the average velocity. The second piece of information I'm given here is that a dog takes 4 seconds. And 4 seconds is a time. And then the last thing we're given is that the dog takes 4 seconds to run 14 meters. And this is a distance. So I'm trying to find the velocity. I'm given in my question a time, and I'm given in my question a distance. So what I can do is I can go to my triangle, and I can use my finger and cover up what I'm trying to find. So I'm trying to find the average velocity. So I'm trying to find that guy. What does it leave me with? Well, it leaves me with distance divided by time. So average velocity is d divided by t. So that's kind of one way to think about it. Another way to think about it is this. This is the equations sheet from the back of your data booklet. If you look at average velocity, here's average velocity is change in position over change in time. This is essentially the same formula. You can kind of, I don't want to say ignore the triangles, but students see those triangles, the deltas in there, and they get kind of like worked up about them. Like, oh my goodness, what does that mean? There's a triangle, it's so confusing. And it doesn't need to be confusing. All it means is you change in your position. So generally speaking, we'll start and end, or we'll start at 0 and end somewhere away from 0. And in terms of time, it's the same thing. Generally, we'll start at time 0 and end, 5 seconds later. Very rarely will we ever have to worry about the fact that we're changing our time or we're changing our position. So you can think of this formula instead of V average is delta T over, or delta D over delta T. You can just think of it as V equals D over T. And that's it. And same here. d equals v multiplied by t, and this is t equals d over v. So they kind of look really intimidating with all the subscripts and triangles and things like that. Really, you can just think about it as time is distance divided by velocity. And you've done questions like these when dealing with density before. So although you probably don't remember, you've done this type of question before. All right, so we have the average velocity, or just velocity, is the distance we traveled in the amount of time it took us to get there. So in this case, the distance we traveled was 14 meters. So I'm going to write 14 meters. And then we're going to divide that by the time. And in this case, it was 4.0 seconds. So 14 divided by 4, it's not going to give us a nice even number. 14 divided by 2 is 7, divided by another 2 is 3.5. So 14 divided by 4 should give us 3.5. And just like last day I said, it's really important to include units with everything. Today is even more important. So what are my units? Well, I have meters here and I have seconds here. So my answer is going to be 3.5 meters divided by seconds, or meters per second. As well as including units, we should include a direction, because it's asking for the velocity. And the velocity wants us to include a direction. And if we reread the question really quickly, it says 4.0 seconds to run forward 14 meters. So I see this forward, and I can include forward as my direction. So 3.5 meters per second forward. What does that mean? It means in a second, the object's moving 3.5 meters. So if I had a meter stick, I could lay out 1 meter stick, 2 meter sticks, 3 meter sticks, another half a meter stick. And in 1 second, the object's going to go from the beginning to the end of that. And that's how fast it's going. So meters per second is an interesting sort of way to measure velocity. That's how we'll, generally speaking, measure the speed and velocity of things. All right, example number 2. See if you can do it without my help. It's almost identical to the one we just did. So a boat travels 420 meters east in a time of 120 seconds. What's the boat's average velocity? Same formula. Make sure to include in your answer an answer. You need units and you need a direction. And it's important as well to show your work. And when, I always forget just because I'm just so used to it, but when you do questions in physics like this, the first thing you need to do is write down an equation. What equation are you using? So show me that you know how to identify the equation. It's not just enough to just do the division. Write down the equation, first step. Second step is substitute your values in. And the third step would be to include an answer with correct units and a direction if necessary. I'm going to write all that down. Step 1, our equation. If I read the question, it's almost the same as this. So I'm interested in finding the average velocity. I have a distance and I have a time. So it's the exact same as the previous one. Average velocity is distance divided by time. So there's my first step. I've written down my equation. My second step is substitute values in my equation. So the average velocity is going to be the distance I traveled, 420 meters east, in the time of 120 seconds. And step 3 would be to write down your answer with appropriate units. So 420 divided by 120, that's not going to be a nice even number. Will it be 42 divided by 12? My brain's not working as well as it should be right now. All right, so let's go. 420 divided by 120 is 3.5 again. Well, that's kind of weird. 3.5 meters per second, and in this case, everything's traveling in the direction of east. So there you go. Generally speaking, a physics question like this in both Science 10 and Physics 11 is going to be worth about 3 marks. 1 mark for each of the steps. Equation, substitution, and then your kind of evaluation of the answer. So you should have kind of these 3 things each question. I don't want to just see sort of this, 420 divided by 120, done. That's not, it's not going to get you sort of full marks. It's good habits to get into, to do them in these kind of 3 steps. Anybody have any questions there? Is that okay? The next question asks, instead of finding the velocity, the next question is asking us to find the displacement. So we'll do these 2. If you're on the ball today, see if you can get this one done on your own. I mean, the math's not terribly difficult, just kind of setting it up. So we have velocity, distance, time. Cover up what you're trying to find. What is the displacement of a bicycle that travels 8 meters per second north for 15 seconds? So the first thing I always do in questions like this is figure out what information I'm given, figure out what information I'm trying to find, and then try to get the correct formula. So it's asking for what is the displacement. So that means we're looking for D. What is displacement? I'm given some information. I see this 8 meters per second. As soon as I see the units meters per second, I know I'm talking about a velocity. So I have a velocity. And then this 15 seconds. 15 seconds is going to give me a time. That's how long something would take. So what can I do? Well, I can either look at my formula sheet and find a formula that already has displacement solved. So I'm looking for D equals, because that's what I'm trying to find, so I could isolate my variable. So let's do that. I can see right here, this second equation already has D isolated by itself. So I could write down delta D is V average times delta T, or I could just leave it as this, D is VT. So velocity times the time. Distance is velocity times time. So that's out of the data book. If I wanted to just simply do this out of this triangle, I would do the same thing. I would cover up the distance, and then what am I left with? I'm left with velocity times time. So step 1 would be writing down my equation. Step 2 would be substituting values into my equation. So my velocity was 8 meters per second north. And I'm going to multiply that by a time of 15 seconds. All right, 8 times 15, it's at 80, 120, I think. Let's do it on a calculator just to make sure. 8 times 15 is in fact 120. 120, and then distance is measured in, or displacement, I guess, is measured in meters. And in this case, things are still traveling in the direction of north. Whew. All right, see if you can do the same thing for the next question. It's nearly identical. You have person, starting line, You have a velocity 6.5 meters per second, and you have a time of 12 seconds, and then it's asking for the displacement. So it's essentially the exact same set of steps. Again, write down the equation, write down your substitution, and then evaluate units, direction, if necessary, in your answer. Take a second, try that one. All right. So in the question, I identified the velocity was 6.5 meters per second. It also included direction with that. It says west. It didn't give it in like square brackets, but it says in the question west. So there you go, 6.5 meters per second west. What is the displacement? So that's what we're trying to find. That's the d. And then it says after 12 seconds. So that's the time it would take. So what we can do is just identify the things we know, the things we don't know. Trying to find displacement, so I find an equation that has already been solved for displacement, or d, and I get d is velocity times time. Plug in the velocity, I plug in the time, I multiply them together, and I get an answer with units, 78 meters, and a direction west, and I'm off to the races. There you go. Anybody have any questions on 3 or 4 here? Things that were confusing, things you didn't understand, things you wanted further clarification on? We just kind of plugging away, things are okay. That works too, Costin. Trying some of these questions on your own might help, though. If you're driving in a car and you glance at the speedometer, what does this look, or what does it tell you? What does the speedometer tell you in terms of the kind of the definitions we've talked about? If you look at the speedometer, is that talking about a distance? Is that talking about a speed? Is that talking about a velocity? Is that a displacement? Is it a something else? So Kyla says speed. Would anybody have a vote for velocity? Would this the speedometer on your car tell you a velocity, or would it tell you speed? Maybe it tells you both. What do we think? Why is it speed? You're right, Kyla, it's speed for sure. Why isn't it velocity? What's the problem with velocity? Why haven't we a velocity meter on your car? Why is it a speedometer or a speed meter? When you look at the speedometer, there's no direction. So if I look down at the speedometer in my car, it says I'm going 50, because I never speed, it's always 50, and I don't know what direction I'm going. Well, hopefully I know what direction I'm going, but my car speedometer doesn't know what direction I'm going. It just gives me a number, 50, 60, 40, 30. So it's not a velocity just because there's no direction associated with it. The next one, at the end of a long trip, you know how far you traveled by recording the odometer. So usually somewhere near your speedometer, there's like a series of numbers that tell you how far you've traveled, and you can set it, reset it at each trip, and it tells you how far you traveled. So if you knew how far you traveled and you knew how long it took, what could you solve for? So could you solve for velocity? Could you solve for your speed? Could you solve for, what else? Let's just go out of the two, velocity or speed. So I know how far I went. I know how long it took. Could I find the velocity? Or could I find the speed? Or could I find neither? It's the same sort of idea as the previous question. We can find speed because we don't, our car, doesn't know the direction we've traveled, or at least when it tells me how far I went and how long it took, it doesn't understand direction. I would not doubt in the very near future cars will have like navigation and all that fancy stuff now. Cars will probably be able to tell you the direction and how far you went in each direction or whatever. But for now, most older cars tell you how far you went. You could look at your watch, tell the time, and you could find the speed. All right, so taking an idea that we talked about last day, we said, okay, if I'm traveling forward, everything's going to be positive. If I'm traveling backwards, everything's going to be negative. What happens if I have a negative velocity? What does that mean? So in the example here, it says the car's velocity is negative 25 meters per second. What does that mean? Can I have a negative velocity? And in this particular example, yes, maybe. Yeah, for sure you can have a negative velocity. Let's pretend everything in this direction is positive. So if I go this way, I'm moving positive, I'm moving positive. What about if I go that way? Well, I'm moving negative. So my velocity is negative when I start going backwards. So if everything in this direction is positive, that means everything in that direction has to be negative. If everything up is positive, then everything down has to be negative. So if I have a velocity of 25 meters per second, but it's negative, it doesn't really mean anything other than I'm just going in a direction that's not positive. So this might be moving to the left. Or it might be down. Or it might be moving to the west. So remember last day we had these kind of like compasses, and we said north, south, east, west. And we said, okay, everything over here is going to be negative, everything over here is positive, everything down here is negative, everything up here is positive. If I have a negative velocity, it just means I'm moving left, or moving down, or I'm moving to the west. It doesn't really affect anything in terms of calculations or anything like that. It's just the negative sign indicates a direction. That's all it does. It's not like I've entered some magical fifth dimension and things are mystical and you don't know what's going on. I know. If you stick with math and you get to university, you start talking about multiple dimensions more than 3. You start talking about imaginary numbers. You can enter these other dimensions. And one really cool thing about science right now is that, and math in general, is that they're using the idea of multiple dimensions to solve equations. So things like string theory and membrane theory kind of incorporates math in more than 3 dimensions to kind of try to solve these equations, to try to make sense of our universe. So at a very basic level, we talk about things forward, positive, backwards, and negative, and we're talking about 2 dimensions. And then when you get into physics 12 or 11, for that matter, you start talking about 2 dimensions and then 3 dimensions. And then when you get further into university, you start talking about, multiple dimensions beyond just the 3 that we live in. And the universe, some of the equations that we use to govern things around us, they are solvable in 4, 5, 6 dimensions. Some of these crazy theories are using like hundreds of dimensions to solve these equations. And anyways, very off topic, but I think it's pretty fascinating stuff. All right, so 2 escalators. Here, let's pretend the one on the right is going up and this one on the left is going down. So we have 2 escalators, one's going up, one's going down. If we were to talk about, we'll say they're moving at the same rate as escalators typically do. How do we compare the speeds and velocities to these 2 things? So what could we say about the speeds of the 2 escalators? And what could we say about the velocity? Speed. Could we say anything about the speeds of the 2 escalators? Do we know anything about them? Just in general, we don't have to associate any numbers with it or anything like that, but they're slow, okay. So we have one going up and one going down. Would the speeds be the same? Would they be different? What do we think? And then the second part of the question is asking about the velocity. Do we know anything about the velocity of these 2 things? So the speeds are the same. One's going up and one's going down. So let's say the speed of the escalator was 5 meters per second. You're going up at 5 meters per second, you can come down at 5 meters per second. They're the same. So in this question, the speed are the same. What about the velocity? Velocity is this vector. It has a direction associated with it. So if I'm going up, that's one direction. If I'm going down, that's another direction. So how could we compare the velocities of these things? Let's put a number on this. Let's say the speed of the escalator is, I don't know, I'll just 1 meter per second. What would the velocity, so let's say it's 1 meter per second as well. Are the velocities going to be the same for the green arrow and the red arrow, or are they going to be different? So, exactly. So the velocity is going to be different. One's going to be 1 meter per second up, and the other is going to be 1 meter per second down. So they're going to be different. They're just going to be the opposite of one another. The one going up is positive. The one going down is negative. They're both 1 meter per second, but their velocity is technically different because one is up at 1 and one is down at 1. Probably just right on this picture. I like that. So this is 1 meter per second up, and this one is going to be 1 meter per second down. So their velocities are exactly the same but opposite. Is that possible to be exactly the same but opposite? I don't think that's true. So they're opposites. One's up, positive, the other's down, it's negative. They're different velocities. Although the speed is the same, velocity includes this direction and they're going opposite directions. It's kind of one of these technicalities between velocity and speed. This might be the most difficult thing we do in this unit. I don't doubt your ability to do it, but it is a little bit different after you see me do it a few times, you might pick it up. But a lot of times we're going to have a speed or a velocity that is in kilometers per hour. And maybe we'll have one that's in meters per second. And we want to be able to compare them. So we spend so much time in math and science up into grade 10 talking about units. And we always have to have the same units. Sometimes it's difficult to compare if we have different units. Like if I said something's traveling at 100 kilometers per hour, and then I said, okay, something's traveling at 40 meters per second. Which one's going faster? Okay, let's think about it. If I take a ruler that's 100 kilometers long, I start at one end, I go to the other end, and I say, okay, that took an hour. And then I take another meter stick out and I measure 40 meters and I travel that whole 40 meters in 1 second. Which thing was going faster? These are both speeds. Can I compare them directly? Not really. It would be kind of helpful if I could convert one or the other into meters per second or kilometers per hour so I could directly compare these things. What do we think? Is there any guesses which one's bigger? 40 or faster, I should say. Is 40 meters per second faster or 100 kilometers per hour faster? Josh is voting for 40 meters per second. And when you really think about it, if I took out like a measuring tape and it was 40 meters long and I traveled that whole 40 meters in 1 second, that's a really big distance. And it is faster, so you're right, Josh. So your intuition was correct. All right, so the first example here asks us to convert 75 kilometers per hour into meters per second. So the process for all of these questions is going to be essentially the same. It's always going to be 2 steps, and the tricky bit is getting the numbers in the right places. Now, because I think it's easy to think in terms of units, what we're going to do is treat our units kind of like numbers almost, and we're going to cancel them out and try to end up with the units that we want. So we're starting with kilometers and hours, and we want to end up with meters and seconds. And you guys could probably sort this out on your own. All right, kilometers. I don't want an answer in kilometers. I want an answer in meters. So I want to convert kilometers into meters. And you guys know how to do that. You guys are good at that. You've done it a lot. So you want to use this little tidbit of information that 1 kilometer is 1,000 meters. Most people remember that. So here's where the units come into play. I have kilometers on the top, but I don't want kilometers in my answer, so I want to get rid of it. In math, if I want to get rid of something, I can divide by it. So if I had like a 2 and an x and I wanted to get rid of the 2, I'd divide by 2. Because 2 divided by 2, those cancel out, and now they're gone. So that's what I'm going to do. I'm going to put kilometers on the bottom. Because I have kilometers on the top and I have kilometers on the bottom. If I have it on top and bottom, they're going to cancel and just give me 1. And that's kind of what we want. I want to end up with units of meters. So I want meters on the top. So I'm going to put meters on the top. And then once I get here, I know the relationship between these things. Conversions, we've done before. I know 1 kilometer is 1,000 meters. We might even have done this example in math. Probably did. Pretty much guarantee we did, actually. All right, so I have kilometers on the top, kilometers on the bottom. They're going to cancel out and just give me 1. I know that 1 kilometer is 1,000 meters. So if I just looked at this one thing, just this thing in the circle, this just equals 1. So all I'm doing is multiplying by 1. How does it equal 1, Mr. Borden? You have 1,000 on top and 1 on the bottom. Well, it's just 1. If I had, a ruler, which was, maybe a ruler's not a good example. If I had a meter stick that's 100 centimeters long, or it's 1 meter long, those are both the same thing. It's both the same distance measurement. A meter is 100 centimeters, or it could be 1 meter. So they're the exact same thing. They're just different units. So everything that I'm multiplying to convert from one thing to the other is just multiplying by 1. And I'm going to do the exact same thing with time now. So I have hours on the bottom here. I don't want to end up with an answer in hours. I want to end up with seconds. So I'm going to put hours on the top because the hours on the top and bottom are going to cancel out to give me 1. That's a good thing. Then I'm going to have seconds on the bottom because that's what I wanted to end up with. Seconds on the bottom, right there. Seconds. And then the relationship between hours and seconds. Well, one hour is 60 minutes. 60 minutes each have 60 seconds. So 60 times 60 is 3,600. So it turns out that in 1 hour, there's 3,600 seconds. And again, this is just one. It's just one. An hour is an hour. 3,600 seconds is 3,600 seconds. They're the exact same thing. They're the same measurement of time. So that's just like multiplying by 1 as well. All right, let's make sure our units work here. I have kilometers on the top, cancels out with kilometers on the bottom. I'm left with units of meters, and that's what I have over here. So that looks good. I have hours on the bottom, and then in my next term, I have hours on the top. They're going to cancel out. I'm going to be left with seconds. So my units of meters per second worked out. Now I just need to do the math. So I'm going to go 75 times 1,000 times 1. And then I'm going to divide it by 1 and then divide it by 3,600. And I should get the right answer. So my calculator, 75 times 1,000. I don't really need to multiply by 1, but I can. And I'm going to see what that equals. And then I'm going to divide that by, I'm going to divide it by 3,600. And I'm going to divide it by 1. Another 1 on the bottom, but of course that's not going to do anything. And I end up with 20.8 meters per second. My units already. So there you go. If I was traveling 75 kilometers per hour in my car, I would be traveling pretty quickly. That's the equivalent to 20 meters in 1 second. So if you're cruising in your car down the highway at 75 kilometers an hour, if you had somebody measure out 20.8 meters next to you, because you're going so fast, you would cover that whole 20.8 meters in 1 second. Or you could have a really big ruler that measured 75 kilometers, and it would take you an hour to cover that 75 kilometers. Josh, I'm going to put you on the spot. Did you get it right? You can lie to me and just say yes if you want. It's fine. Thank you, Josh. So there you go. Let's try another example. Same thing. 95 kilometers per hour to meters per second. So I initially used the 100 meters per second. And then I said 100 kilometers per hour or 40 meters per second. Which one was faster? This will figure it out for us. All right, so I'm gonna need to convert my kilometers into meters. And then I'm going to also need to convert my hours into seconds. Why is kilometers on the bottom? Because it's going to cancel. I should do that in red. Y is hours on the top, so it's going to cancel. And I'm going to be left with meters, and I'm going to be left with seconds. And that's what I want, an answer in meters per second. What is the relationship between these things? 1 kilometer is 1,000 meters, and 1 hour is 3,600 seconds. So the math here is going to multiply all the tops together, and then I'm going to multiply all the bottoms together, and I'm going to divide the top by the bottom. In terms of sort of math, because there's lots of ones and whatnot there, all I'm doing is going 95 times 1,000, and then I'm going to divide that by 3,600. And I end up with 26.38 or 20, we'll call it 26.4 meters per second. That wasn't what I was hoping to happen. Okay, so 95 kilometers per hour. It's 26.4 meters per second. We have 2 questions left here, and that's it for 8.2. I'll do this next one with you, and I think the last one, yeah. I'll do this one with you, and then we'll look at the learning guide. We'll take a bit of a break. A truck's displacement is 45 kilometers per hour north. After driving for 1.3 hours, what was the truck's average velocity in kilometers per hour and meters per second? So again, kind of getting back to what we were doing before, the question we're asked here is trying to find the average velocity of the truck. It's asking for kilometers an hour and meters per second. What else do we have in the question? Well, we know it takes 1.3 hours, so that's a time. And it says our displacement is 45 kilometers. So I need an equation that has V is equal to d over t. If I jump over to my data book here, I see the very first question or first equation I have there is V equals d over t. So that's what I'm going to use. All right, so the velocity, the distance I have is 45 kilometers, and I have it in 1.3 hours. So my units here are going to be kilometers per hour. So my answer is going to be in kilometers per hour. I don't know what 45 divided by 1.3 is, so I'm going to refer to my calculator to help me on that. 45 divided by 1.3 is going to be 34.6 kilometers per hour. So that's great. Do I have a direction? Truck's displacement 45 kilometers north. So if my truck is moving north, my velocity will be north as well. The second part of the question asks me for my velocity in both kilometers per hour and meters per second. So I have 34.6 kilometers per hour, and I want to convert that into meters per second. So we've done this a couple times now. We can look up above. I have kilometers on the top. I want to get rid of it. I'll put it on the bottom. I have hours on the bottom. I want to get rid of it. I'll put it on the top. 1 kilometer is 1,000 meters. 1 hour is 3,600 seconds. So what I'm really doing here is going 34.6 times 1,000 divided by 3,600. And I will point out this one little thing, that if I looked at everything in the brackets and I want 1,000 divided by 3,600, essentially, I would just be dividing by 3.6. So there's a nice little trick here, if you're with me. 34.6, we can just divide by 3.6, and we're going to get 9.61. Or I can go 34.6 times 1,000 divided by 3,600 is 9.6 as well. Just a little math trick. And again, this is north. All right, that's a lot of talking from me. Let's look at the learning guide here. We've done all that stuff. So velocity, list all the motion, kinematic equations from your formula sheet. So those are all there, just look them up. List every equation with a variable. So what does D mean? What does V mean? What does T mean? Give units. Average velocity, instantaneous velocity, you guys can do that. And then 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 are all just sort of calculation type questions. So it's 10:30 right now. The next section's on graphing. So what do we have left? We've got 3 sections left. We've got graphing, we've got acceleration, Unit 9. Trying to think of how much time we'll have to finish all this stuff. So what I'll do is this. I'll give you guys 20 minutes to just work away on some of these questions. And we'll come back at the end of the 20 minutes and I'll answer any questions you guys had on the velocity or 8.2. We'll start next class with 8.3, which is graphing. And then we're just going to have a weird break in there somewhere. So next day we're actually going to finish off Unit 8 and then start Unit 9. Unit 9 is only 2 sections, so we'll finish Unit 9 next Thursday. Next Thursday gives us a week for review. Yeah, that'll be fine. I don't think, does anybody want to do graphing today? How many slides is this graphing stuff? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, you guys aren't gonna, you're not gonna want to do graphing today. All right, so I'll give you guys 20 minutes to go through the learning guide on section 8.2, the velocity. There's like 16 questions. Some are just kind of vocab, some are actual calculations. Use your data book, use the formulas out of it. In 20 minutes we'll come back, we'll meet, and I'll go through any questions you guys had. And then we'll call her a day there. Next class we'll finish up Unit 8, doing the graphing stuff. And then we'll move on to the beginning of Unit 9. So we'll do 2 sections on Tuesday. Thursday's class next week, we'll do the second section of 9.2. There's only 2 sections in Unit 9. And that'll be it for Unit 9. So we'll be done the course on a week from today. Gives you a week for review. And then it's the 12th through the 20th. Yeah, a week and a couple days for review. And then you guys have your final exam the following week. So that makes sense to me. Hopefully that makes sense to you. There you go. 20 minutes to kind of work through these questions. I'll see you guys back here, and then we will go through any questions you might have. Thanks. All right, guys, welcome back. A lot of questions there. Did anything come up that was a little bit tricky, something you didn't understand? The first few are kind of definitions, but then you get into some of the other calculation type things. Nothing? No questions? You guys are all just experts at this stuff? That's what I like to hear. Did such a good job at teaching it. Nobody's confused. How about this? Can you give me a green check if you can hear me, just to make sure that I'm still talking to you and you can yeah, all right, thanks, Josh. All right, good, good. Okay. Well, if nobody has any questions, then I'm not just going to do a bunch of questions for the sake of doing questions. So I'll leave those with you. Remember, when you're doing these, when I'm going to be marking your learning guide, I'm looking for three things. Looking for the equation you used. I'm looking for you to substitute the correct values into the equation. And then I'm looking for your answer with units. And then if your answer is a vector, units and a direction as well. So those are kind of the big three things I'll look for each of these questions. That requires work to be done. Some of them are obviously just definitions and whatnot. So that's pretty straightforward. Today's Thursday, that means tomorrow's Friday. We're going to do a hike tomorrow at Bear Creek Park. I just want to get the correct time up here. There we go. 11 o'clock tomorrow, Bear Creek Provincial Park. If you've ever camped at Bear Creek before, it's not the campsite, but you're across the street on the other side, let's get my directions right, the west side of West Side Road. If that makes any sense. There's a little parking lot and a couple, like an outhouse, and we climb up the hill, big loop. It's like a kilometer or two or something like that. So we did it last year. It was good. It's a good hike. With all this rain last night and again possibly tonight and the snow melt from up above, the waterfall will probably be moving pretty good. It's raining now. That's good. The waterfall will be spectacular tomorrow. That's why we do the hike. There's a big waterfall. So it'd be really nice to see you guys out there. Pretty low impact activity, just walking. Get some fresh air, connect with some peers. It'd be good. So that's tomorrow at 11. Hopefully I see a couple of you guys there, or all of you would be even better, but some of you. And next day on Tuesday, we're going to continue with Unit 8. We have one section left on graphing. We're going to talk a little bit about slope of lines and just describing motion with graphs. And then we'll do acceleration as well as the graphing stuff. So we'll do 8.3 next day as well as 9.1. So next class, you should have Unit 9 learning guide printed off, and we'll go through the beginning of that. Then Thursday's class, we'll do 9.2, which is acceleration again, and that's it. So next Thursday, a week from today, we'll finish the course, and that leaves us some time. Got a calendar here. There's June. So that's next week, and that gives us 2 weeks for a review, essentially. So if we finish on the 8th, it gives us our finals on the 21st. So there you go. That's what the next couple weeks is looking like. I will, before Tuesday next week, I'll have the final exam done, so I can tell you exactly what that is going to look like. I will also have all of the review material printed up and loaded online. That'll give you 3 weeks to review, and that should be plenty of time. Not that you'd need 3 weeks to review, but just in case you want to get on it ahead of time, there you go. If nobody has any questions, we'll just leave it there, and I will see you guys hopefully tomorrow. If not tomorrow, then again on Tuesday's class. I don't see any questions. So thanks very much, guys. Enjoy your weekend, and we'll see you later.